worksheet, the most important things for you to know, I think, about RC and RL circuits. So we're also going to be looking at Thevenin because I had a lot of questions, people asking about Thevenin. So we will be looking at that. But these formulas right here are, some of the key ones for you to pay attention to. Now, you have in your book the formula for, say, voltage across a capacitor, and you have that do I have the wrong pen? You have that VC of t, for instance, equals VC at infinity plus VC at 0 minus VC at infinity times e to the minus t over tau. Okay, and so this, hey, how'd y'all get in? Oh, that was nice. Did y'all text me? No, you didn't. You did text me.
I was at the wrong building.
Oh, okay. All right. Okay, so you have this formula for the voltage across a capacitor, and you know that to get the current across a capacitor, the current across a capacitor is C dV dt, so you can get that, and that is often how I do it. And you have a similar formula for the current across an inductor, but this formula right here is kind of a general formula for a first order circuit. So a first order circuit, we're talking about a circuit that has a capacitor or an inductor, but not a capacitor and an inductor, and you can fill in this X with current or voltage or whatever you need for your particular problem. And the F means final, so like at infinity, and the T0 means initial, or at whatever time you're starting. And this minus T naught is just in case you're not starting at 0, but I suspect you will always be starting at 0. So you could change this to e to the minus t over tau, just knowing that that's meaning that you're starting at 0. So those are the formulas that you would use most often for an RC or an RL circuit. So let's take a look at the first problem that was on the old test, which was to find the Thevenin equivalent of a circuit. And at any point you'll need to call out if you have a question. If you're on Zoom, I'll try to take a look at the chat, but I often miss it. It's better if you just say something. And if you're here, please ask questions. It's better if you ask questions. All right, so first of all, we need to know what a Thevenin equivalent means. So a Thevenin equivalent has to do with you have a particular part in your circuit. Usually it's where you will put some sort of load. A lot of times it's called RL for resistor load. And you want to simplify the rest of the circuit so that the rest of the circuit looks just like a voltage source and a resistor for Thevenin, or a current source and a resistor for a Norton. And when you do that, you're just saying that you don't really care about how the circuit works. You just need to know how it affects you. And the way it affects you, if you are the resistor in that place, is by what the voltage is and what the resistance is. So you have different techniques for finding the Thevenin equivalent. And unfortunately, when you have a dependent source like we have here, then you have to use a technique called the external voltage technique, which is the least fun technique. We'll look at the other techniques or whatever else I would use later, but we're going to use the external voltage to solve this one. So for almost all of them, you are going to find what's called V open circuit. V open circuit is also equivalent to V Thevenin. So you look at the place where you're told to find the Thevenin equivalent, you make it an open circuit, and you find out what is the voltage across that open circuit. So for this circuit right here, what we're saying is we are looking at, if this goes away, right here, what is the voltage across that this terminal right here? What is V0 when we have an open circuit? And that will be our Thevenin voltage. And so you find that using any of the techniques that you've learned previously in this semester to get the voltage. And so there's different ways of doing this. I did it before I realized that he had posted solutions. And so the way I'm going to do it is not exactly the same way that he did it, which is on purpose because it'll give you can look at his solutions and see how he did it. You can watch this video or watch me and see how I did it. And you can say, oh, well, I might do it a different way altogether, which is fine. There's always a lot of ways to do it. And so this way you'll get exposure to more than one way of doing it. So what I noticed was in this circuit, we had our dependent current source right here was 2Ix. And when this is an open circuit, you can see that there's no current coming down in this bottom branch. There's no current there at all. So all of this current is going here. And so I can do a little KCL at this node right here. So at this bottom node, KCL, I can say that the currents coming in have to equal the currents coming out. And I will call this current going up, I'll just call that I1. And so coming in, I have 2Ix. And going out, I have Ix to the right. And I have I1 going up. And so I know that I1 is 2Ix minus Ix, which is just Ix. So I have that. Now, I also can see, if I look at this bottom right-hand corner here, this is Ix in this direction. This is open. The whole point of V open circuit is that it's open. I have a current source right here saying that I have 2 milliamps going in that direction going down. Well, it's the same current. They're in the same place, and they're in series. And so Ix is the same current as this 2 milliamps. It's drawn going in the other direction. So that means that as drawn, Ix is minus 2 milliamps because it's going the opposite direction from the 2 milliamps. So we have Ix going this direction, but we know that equals 2 milliamps going in this direction. So Ix going in this direction must equal minus 2 milliamps because we know it's really going in the other direction. So then that tells us, since I1 equals Ix, I1 is also minus 2 milliamps. And we can use that information to find out our voltage. So we now have enough information to find the voltage. I don't think I actually needed the I1. I just needed to know what this current was. We said there was no current flowing through this bottom branch, and there's no source on it at all. So I can call this ground. I can make that 0. And since that's 0, let's see, what else do I know? I know that I have that's the external 7. Let's look at this voltage right here. Somehow, when I did this before, I just looked at it and I had the answer. Did I do? Yes. Yes. Okay, so this is 0 volts right here. That's 0 volts right there. We know that this current coming down is 2Ix, and so the current going in this direction is negative 4 milliamps. And so the voltage change across this resistor right here, V equals IR. The voltage change across that resistor is V equals minus 4 milliamps times 1 kiloohm, or a milli times a kilo cancels each other out, or minus 4 volts. So that means that this right-hand side is minus 4 lower than the left-hand side, or it is at 4 volts. So it's at 4 volts because we know the current is really going the other way. Because the current is negative 4 milliamps, we've drawn it in this direction and said it's negative 4 milliamps. We know current goes from high voltage to low voltage. It's really going in this direction. So this side must be at a higher voltage. It's at 4 volts. This one's at 0 volts. And then similarly, going across this resistor right here, we know that that current is Ix. And using Ohm's law, we have V equals IR. Our V equals minus 2 milliamps, because that's what Ix is, times 1 kiloohm. Our V is minus 2 volts. Or the other side is minus 2 lower, which means minus 2 is plus 2. So this side is at 6 volts. So relative to ground, it's at 6 volts. And so V Thevenin is 6 volts. Okay, so now we have the Thevenin equivalent voltage. The next thing to find is the Thevenin equivalent resistance. It's a lot easier when you don't have a dependent source. When you have a dependent source, it's a little harder. I want to pause here and see if there are any questions. I have, anybody have any questions? Yes?
How did you determine the node below the 2Ix is 0 volts?
Right here, because it's connected to this, which is I made ground. I made that my reference node, and there's no current flowing through this. And so everything up until where I get to an element is all at the same voltage. Anything that's connected by a conductor is at the same voltage. And if there's no current flowing through it, then it's not going to change the voltage. This resistor's not doing anything. So since I made this ground, that was also going to be 0 relative to ground. Really, what I know by doing Ohm's law is that this side is 4 higher than the other side. Any other questions? Okay, so here is how we find oh wait, let me check the chat. If I can. Nope, nothing there. Okay, so here is how we find the Thevenin resistance when we have a dependent source. Okay, so what we do in this instance is we put something, and you only have to do this when you have a dependent source. You put something called V external right here. So I'm going to put a voltage source right here, and I'm just going to call it V external. It doesn't matter what the voltage is. If you wanted to actually give it a voltage, you could. I am not going to in this problem because I don't need to in this problem. But you could make it 1 volt. And what you're going to find out is that R Thevenin is going to be V external over I external. So you find the current going through that external voltage source, and you take V external over I external, and that is R Thevenin. So that is what we are going to try to do. But when you find a Thevenin resistance, you get rid of all of your independent power sources. And this is going to be true through all of your methods of finding Thevenin equivalence of Thevenin resistance, is you get rid of independent power sources. And here's how you do it. You make voltage sources shorts, and you make current sources open. You have to leave dependent sources alone. But this is the part that helps you because you get rid of parts of your circuit. So when we redraw this, we have to keep our dependent source. Our bottom branch is now no longer open, so it is going to play a role now. But this current source becomes an open source. An open circuit. So the current source becomes an open circuit. So what that really means is that this corner of the circuit is no longer playing any role. So it's no longer part of what's affecting anything. So we can ignore it. And what I can do is I can see that I have the way he did it, I think, with nodal analysis, and that's almost always what I use. But in this instance, I decided to use mesh, and so I'm going to use mesh. And so I have one mesh here and another mesh here. And I'll call this top one I1 and this bottom one I2. Now you'll notice by doing this that IX, the way I drew it, actually I think I want to go the other direction. The reason I want to go the other direction is to make it match my IX. And then it's just easier if you make both of your currents go in the same direction. Much easier. So I'll go this direction. So this is I2, and IX is going right here, and its IX is not shared with any other branch. And so I2, IX equals I2. And notice that I1 is going the opposite direction of this dependent current source. So I1 equals minus 2IX. Okay, so now if I write my mesh equations, remember the way you write your mesh equations is if you're going, you follow the little path that you took, and going into a voltage source, you take the sign of the terminal where you enter. Voltage change across a resistor. is I times R. A shared resistor will be, for example, if I'm doing my I1 loop, it would be I1 minus, for instance, I2 times R. So if you have a shared resistor, you have to include both currents. So if I look at my top loop, I don't really have anything I can do on the top loop because I already know my source there is a current source, and the current source just tells you what I is. So for the top loop, I just have that I1 equals minus 2IX. That's all I have for the top loop. But for the bottom loop, I'm going to go, as I travel along here, I have that, I'll have I2 times 1 kiloohm plus, now this is a shared branch right here, so that would be I2 minus I1 times 1 kiloohm plus, and then on this one right here, that's just I2, so that's I2 times 1 kiloohm. And then I'm going into the positive terminal of my external voltage source there, so that's plus V external equals 0. So that's 1KI2 plus 1KI2 minus 1KI1 plus 1KI2 plus V external equals 0. And that gets me, let's see, and I2 was what? I2 was IX. So 1K times IX plus 1K times IX minus 1K times minus 2IX plus 1K IX plus V external equals 0. So that's 1, 2, 3, 5. 5KIX equals V external, or V external over IX equals 5,000. And what I'm looking for is V external over I external. Well, let's take a look at our circuit. IX is in fact the current that goes through my external voltage source. And so I found it.
Negative capacitance?
You can't have a negative resistance.
For the so you have the external on the same side. So then if you move it over, wouldn't it be negative?
Oh, yeah, so what did I do wrong? No, I'm not, oh. Let's see what I might have done wrong. Okay, so I will figure out what the deal is and why this is, I mean, because you can't have a negative resistance, so, but R Thevenin is 5 kilo ohms. May seem weird, but things are always different when you're like in front of a group of people talking and stuff that just normally makes sense doesn't make sense. But so here is the deal. So if I have any circuit, here's my voltage source, here's my resistor. What direction does the current go? The current goes that direction. That's the direction of the current. And so the voltage is higher on this side and lower on this side, and the current travels from high to low, and then it gets to the voltage source, and the voltage source's job is to push the current across. So that's what it does. So when I'm talking about V equals IR, then if I have a voltage source that's 12 volts and a resistance that is 3 ohms, then my current is 4 amps, and it goes in that direction. So when I am looking at this particular circuit, V external, and I am trying to find I external, then I am looking for the current that goes in this direction. So because that is the direction the current goes. Because if I'm trying to find R Thevenin, that comes from Ohm's law, V equals IR, so we're talking about the current that would come out of that voltage source. And so what direction does IX go? IX goes in the other way. So when we got to this, just in my head, I was like, oh, I knew resistance was positive. That's why I made that mistake. So we get that V external over IX is negative 5,000, but I external is actually minus IX because it's going in the other direction. So V external over I external is 5,000, positive 5,000 ohms, and that's what we needed. So R Thevenin is 5 kilo ohms, and we had found earlier that V Thevenin was 6 volts, and so our Thevenin equivalent circuit is that you have a 6-volt voltage source and a 5 kilo ohm resistor, and this is your Thevenin equivalent circuit. And then part B of the question was, if R1 equals 1 kilo ohm, find VO. So that would mean, going back and looking at what the circuit looked like before, and that would be if R1 is right here, and we have VO here and here, and if R1 is 1 kilo ohm. Well, this is easy. There's a couple ways to do it. One way to do it is to find the total current and then use Ohm's law. Another way is just to use voltage division. So I have a total of 6 volts change across both resistors. And so the voltage across R1 equals my total voltage change times the resistance of R1, which is 1 kilo ohm, over the sum of my two resistances, 5 kilo ohms plus 1 kilo ohm, or 6 volts times 1 over 6, or 1 volt. So that's the voltage across that one. Yes?
Are you planning to go over any more like going in better
I did have another one, yeah. Yes.
Push up just a little bit, where, so, I was just curious why everything goes from I2 to IX.
Because back here, the way I drew my loop, I called this I2, and IX was right here. And so I2 equaled IX. So I just did that replacement. And then also, I had I1 right here. And I1 is going in the opposite direction of this, so I1 was minus 2IX. So that was why. Okay, other questions? All right. I am going to stop this recording.